Dr. Khot. He's an assistant professor in the Department of Biological Systems Engineering at Washington State University and is also affiliated with the Center for Precision Automated Agricultural Systems. Dr. Khot received his PhD from North Dakota State University in 2009, and prior to joining Washington State University, he was a postdoctoral researcher at the Citrus Research and Education Center at the University of Florida. And as Dr. Khot's title mentions here, beyond the domain of small unmanned aircraft systems, which we all are probably aware would be beyond 55-pound threshold. So with that, I'll go ahead and turn the program over to Dr. Khot.
All right, so thank you, Dr. Volt, for the introduction and starting with the topic. So for next 20 minutes or so, I'll be just discussing or initiating a discussion on the domain of mid-size unmanned aerial systems and what it means in terms of doing the precision agriculture in the United States, right? So before I go into the topic, I just wanted to get to the acknowledgements first. So first, of course, so for today's talk, it's in two sections. The first half of my presentation would be on the general aspects of mid-size unmanned aerial systems, and it's some of the general applications, general requirements of this system if we have to do precision ag applications with such platforms. The second half will be specifically on one of the projects that we are doing here at Washington State University, and for that the project is funded through WSU's Emerging Research Issues. So the team here is, of course, besides myself, Dr. Troy Peters, Dr. Whiting, Dr. Zhang, and Professor Granstein, who are part of this project. Most of the work on this project is done by the postdoctoral associate, Dr. Zhenfeng Zhao, who is working with us. And of course, we have very good collaboration on this project. For part of the project where we develop in-field sensing system, we have support from Decagon Devices. For the unmanned aerial system part, we have the collaboration with the Digital Harvest, which in turn collaborates with or is trying to introduce Yamaha in the Pacific Northwest. I should mention here that for this project, so the interface is, of course, the introduction to the Digital Harvest was made by my postdoctoral advisor and my mentor at the University of Florida, Dr. Isani. So I just wanted to acknowledge him here. And of course, some of the people from my lab who worked on doing the field trials that we did here, right? So, okay, so let's get started. So we know that precision agriculture, we have different components. Of course, we have, when we talk about precision ag in row, field, or tree fruit crops, we started with all this process with global positioning system, which we can use to the guide or navigate the agricultural vehicles or platforms in the field. The key component, of course, is doing sensing to understand the variability in the field, and this, so it has to do with using the proximal remote sensors or some other sensors, and of course there we heavily relied on the satellite data. Of course, the small unmanned aerial systems are pushing that boundary further, and then we are now at the level where we get very high quality, high resolution data to understand the variability in the field at much higher level. So that being said, we have been talking about small unmanned aerial systems for last few years. The industry is dynamic and it's rapidly expanding. So of course, that's just one aspect of precision agriculture, doing the sensing and understanding the crop variability. So when it comes to do the variable rate application, we have, of course, we are using a lot of ground vehicles. We have so many variable rate technologies that are developed for row and field crops. Slowly it's creeping into the tree fruit. But for today's discussion, I wanted to start the discussion and get the perspective going on the aspects of how can we transfer or transform from the ground to aerial to do most of the variable rate crop inputs in most of the crops that we grow in the United States, right? And of course, the last component here is the yield monitoring and mapping, which is also key part of precision agriculture, which again is kind of has been rapidly changing because of the use of small unmanned aerial systems. But for today's talk, I heavily want to discuss the small mid not sorry small but mid-size unmanned aerial systems, which are, as per the Department of Defense and the FAA, it's the platform that is beyond 55 and up to 1,000 pounds, right? So when we are talking about the transition of the ground-based variable rate application or any other thing that we want to do in production management to the air, what it means in terms of having the platform of that size, right? So of course, just like a tractor, we need something that can lift heavy payload, right? So we are talking about doing the spraying, doing crop dusting, doing variable rate seeding, and all these applications that I will discuss a little bit later. So to do this, we need something that can lift heavy payload, right? Not just 5 pounds of optics and just do the imaging, but beyond that. So again, if we have to have such kind of mid-size system, one attribute that is needed, in my opinion, is we need to have such platform which is can have versatility of attachment. So it can in one go we have the sprayer system there, and then it just snap out and we put something else, strap this with optics and do the remote sensing, strap this with the dusters and do the dusting, things like that. So that's another attribute that is needed. We know that small unmanned aerial systems, we have issue with the flight time. Of course, the fixed wing can go up to 1 hour, but the rotocopters can go up to like half an hour or so max. But if we have to do the field operations more than imaging, we of course lifting that heavy payload, we need a platform that can fly at least an hour or more, and that's one of the attribute is key. Of course, as one of my friend, Mr. Yong Kim, who is collaborator on this project, we have some discussion on this, and in his terms, the night operations using the unmanned aerial systems will be the game changer for doing the agriculture, right? And it's very simple, right? If you think about doing the spraying, we know that spraying of the row, field, or tree fruit, if it's a stable boundary layer condition, we know that the deposition is going to be good, coverage is going to be good. Also, there's going to be less drift, right? And so we know that for better part, the stable boundary layer conditions of the atmosphere exist during the night time, right? And so, of course, some of the research that is done out there in terms of yield monitoring and yield estimation, if we do the imaging in nighttime, it's a lot better than doing in daytime. So, of course, if we have this platform which can be operated in nighttime, right, autonomously, that's going to change the game of the how we do the ag production management, right? So, of course, when we are talking about agriculture, we need to have such platform with vertical takeoff and landing, because if there is a restricted space, there's not going to be a paved runway for all the fields. So, one of the attributes that is needed is the platform should take off vertically and land vertically, right? And the last the attribute that I think is important, and of course for the audience here, we don't need to talk about what is fail-safe configuration, but so when we are flying this heavy payload platform up in the air, things can go wrong. So the first and foremost attribute that is needed is, again, having that robust fail-safe configuration, right? And so if we have that kind of platform, then we can do a lot of agricultural production management with such platforms in near future, right? So what's out there, right? So unfortunately, not much, right? We know that the Department of Defense, we have the unmanned aerial systems which can lift heavy payload, but when it comes to agriculture, there are not many platforms that can be used right away, right? So One of the platforms that's out there and that we are using on this project that I'll talk about in a while is the Yamaha's RMAX, right? And this platform is being used in Japan for last 20 years or so, doing a lot of rice production management. Another platform that's out there and which is not yet retrofitted or modified for agriculture, but there's a plan to do so based on my communication with the gentleman Paul Morgan from the east, is it east? I think West Coast, right? Yeah. So this is the DP14 Dragonfly, right? So this is a dual rotor and it can lift a lot more payload, and the company has plans to modify this for doing agriculture applications, right? And these are just two platforms that I came across, but there might be many more, but which I'm not aware of, right? So in terms of applications, right, from the Yamaha's RMAX and some other platforms, they are being used for some of the applications such as doing the aerial seeding, doing the top dressing of pastures in row and field crops. Yamaha's platform is heavily used in Japan to do the dusting and fertilizer applications, right? So some of the other applications that I think these such platforms will be useful is we know that of course in Washington and there might be many more places that we get when the trees are coming out of dormancy and the birds are coming out, we have the cold nights and sometimes temperature drops below freezing, and then we have the issue with the frost, right, and our freezing of the birds and the damage because of that. So and in Washington side, in Pacific Northwest, we have these wind machines sprayed across every 4 hectares or 4 acres, who invert the air and who try to avoid that damage. I think instead of having such fixed installations, if we have this platform that can do more than one thing, if we can use such platform to do this frost management, that could be one of the unique applications that we will have. Of course, the key application of such platforms in precision ag would be doing the surgical spraying. And by meaning surgical spraying is we need to know, of course, we have this remote sensing going on now with the small UAS. What we need to know is where the problem is of the pest or disease in a given block of the field, and just apply the chemicals at that location than spraying the entire block. And that will save a lot of chemicals, a lot of monetary benefits to grower. And also what that means is we are not damaging the ecosystem to the level that it's becoming more of a sustainable farming then, right? So that's that. And so another application that which I'll be talking about from next slide on is using such platforms to do the crop loss management, right? And this is one of the unique applications that we are doing, which what I think, but we'll see, right? So let's get started on that one. So this is about sweet cherry, right? Reducing the crop loss management in sweet cherry production, right? And so if you see the sweet cherries sometime in June and July in fresh market in Walmart or Costco or some other places, right? They are either from Washington, Oregon, or from California for a better part. So here in Pacific Northwest, we have about 75% of total US fresh market sweet cherry production, right? And so it's a huge deal for the growers here. It's a specialty crop, of course, and it's a high value crop. The issue with this crop is that during last 2 to 3 weeks of production, right, before harvest, what happens is, just like anything else, we have these seasonal summer rains, and the issue is the fruit is the cherry fruit is maturing, right, and so it has high sugar content, and the skin is thin, and because if there is a rain event, because of the rain event, the skin will split or crack, right? And so that's one of the major concern. If we have to ship the fruit or the cherries for fresh market, no consumer will accept such fruit, right? So growers, they are emotional about this, and they do all the things that they could to avoid such splitting, rain-induced splitting or cracking, right? So there is another hypothesis to this, that in the same last 3 weeks period, if there is increased water uptake by the plant root, and that also get transmitted to the fruit, and then there's splitting or cracking. But for today's talk, let's just focus on the rain-induced cracking, which is the major part, because growers know how to control the irrigation in last 3 weeks, but the mother nature not always helps in terms of not having the rain there, right? So what growers do, of course, in South America, a lot of growers there, they use canopy covers, but the canopy covers are expensive, right? So in Pacific Northwest, what we do here is we spray the calcium chloride based products out there before the rain, and sometimes it get washed out, and then again we spray another round of the spray. For better part, most of the growers who have the money and then access to such platforms, they use the manned helicopter flights to shake the canopies to disperse the water from the canopies so that the fruit will not crack, right? And so the business is good here, right? So if you have money, the grower can lease such platforms, and what's involved is you are paying about 20,000 or more to lease such platform, and then the flying hours are extra, right? So and the helicopter is parked at your site, your orchard, and if there is a rain event, of course no pilot will fly in the night time. They have to wait for the morning, and then they will just disperse the water to avoid the fruit cracking, right? So the small growers, what they do, they use because they don't have access to the helicopters, right? So they use the orchard sprayer instead of spraying the water. They just use the air blast coming out of such sprayers to shake the canopies and remove the water, right? So on this project, right, what we are doing, of course, growers have their years of experience, and they know, in what scenarios water needs to be removed. What's not out there is there's no quantitative information on how much water is there to begin with, and at what rain level, and then how much water gets removed because of the pass of the helicopter or orchard sprayer, right? So the key component of this research is developing such kind of decision support system using the in-field sensors to let growers know in real time what's out there, the wetness, how much is there before and after any use of any of this treatment, right? And unfortunately, right, so when we are talking about the manned flights, they have to fly about 25 feet or so above the canopies, and it's not always safe, because if you have seen the Washington terrain where the orchards are, and it's not flat orchards like Midwest. It's all on the slopey terrain, and so it's not safe. Let me put it that way. And every year we have 1 or 2 accidents, and there are human lives that have been lost. So to that end, what we wanted to see is, can we use this? Another component of this research is to use Yamaha's unmanned aerial system, or the helicopter that is 1/3 of the size of any normal helicopter there, right? To see how efficient it is to begin with to remove the water from the canopies, right? So the first part, developing the in-field sensing system, we have support from Dikagan devices, and we have instrumented the orchards with the leaf wetness sensors and the anemometers and the temperature humidity sensors, and there are some accelerometers we're using to see the alternative approach to use the wind sonic anemometers and things like that. And so we have all the instrumentation that was made in 2014, and we tested all this for data transfer and everything. And so after that, 2015 season, right, we did the study that we are talking about today. Of course, by the time Yamaha got the permission to fly in US with 333 exemption and everything, by the time the real action happened, we were a bit late. The fruits were harvested from the canopies, and so we did all the experiments just to see how much rainwater gets removed, or how much the shaking happens and what is the downwash and everything. And we didn't really relate this data to the cracking, so that's I should put upfront. So again, in terms of what we tested is, if you have seen, for just like any other crop, tree fruit, most of the traditional trees are being replaced with this modern architecture. We have a lot of vertical trees, vertical upright uproot systems. There's also the Y trellis architecture where the trees are grown in Y shape. And so these are the modern architectures that are being designed for ease of mechanization and things like that. And so we have done the tests only in these two types of architectures that are becoming more of a norm here in Washington State, right? So in terms of water removal, we tested again the air blast sprayer, the crosswind of the air blast, and the downwash from the unmanned aerial system of the Yamaha's platform. But for today's talk, let's just focus on the downwash, right? So, and again, we here what you see here is a rain simulator, because when you want rain, it's not there, right? So we have to simulate the rain. So we use the rain simulator to wet the canopies and dry it with the downwash. So let's run the video if we can. Okay, so this is the instrumentation that we have in the orchard to begin with. And is there a problem here? Yeah, I think it's from my end, it's a problem here to download it. Oh, okay. So I think it will not go well. What it is I just wanted to show, to maintain the FAS line of sight, what we did, the way we simulated the rain, and then the way we did the test. One of the tests we did is in static mode. We wanted to see at what altitude we should shaking happens in the canopies there, and things like that, and how we operated this. But I think on my end it's not downloading properly. Hopefully you are seeing it, but let's just stop it for that in respect to the next speaker, right? So I'm just going to go from the. Can somebody help me to get the video out of the screen, please?
I can take it away. The rest of us are seeing the video right now.
Okay, well, thank you. Yeah. So, okay, so I hope the video was working. But then what you see here is in the static test, what we did is we have the helicopter, the mid-size helicopter 4 at one location, right? And then we went upwards right from the about this is 15 feet to 25 feet up we went, and we had instrumented the canopies with the anemometers at two heights and vertically, and at different locations horizontally. We just wanted to get feel of how much downwash is created at what height, right, above ground level. And so the bottom line is what we figured out from this test is, of course, if we tested two things. One is with payload and without payload. So what that means is the base weight of the platform is about 64 kg to begin with. And so if we add the spray tanks, we can increase the payload up to 80 kg, right? So in that configuration, is there any change in downwash and how much it is, right? So of course we found out that with payload there is higher downwash compared to without payload. And when we fly this at different altitudes, of course the downwash kept increasing, right? And so up to the 7.5 meters we went up in the air. The take-home message here is, of course, to cover this canopy, we wanted to see how much wider the downwash happens effectively down to the bottom line of 4 meters per second, right? And so what that means is, here on the one side we are getting downwash up to 1.3 meters, and that's the cutoff here. So effectively, we can cover about 2.6 meters in one go, and that means we can cover one row at a time. And so if we are thinking about manned flights, it's about 3 rows in one go, right? And so so in terms of the actual tests, what we did, we of course have the with payload and without payload condition to test with, and then we tried 2 travel speeds of the helicopter, that is 1.3 meter per second and 2.7 meter per second. This is about 3 and 6 miles per hour, right? And the platform was flown at 3 different altitudes above ground level, right? It's about 5 meters, 5.5, and 6.1 meters, and all these treatments were replicated. And then, of course, we had a control to know how much canopy drying happens without doing any downmesh, right? So the data that is presented here is coming from the leaf wetness sensor, right? And so when the leaf wetness sensor is dry, the readings of the canopy wetness is 0. When it's saturated with 0.1 inch of rain, which is what's simulated here, we had 100% saturation. And then we had the treatment happening, and then we looked at 10 minutes after the saturation, what is the rainwater removal rate is, right? And so of course, if you see in both, like with payload and without payload, we have higher rainwater removal with payload conditions. And what's happening here is we tried, if you see here, the height above ground level, if we are flying too close to canopy, it's like 5 meters above the ground level, we are not removing much of the water, right? But if we are flying anywhere between 5.5 and 6.1 meters, then we are getting good rainwater removal in with payload and without payload condition, right? And so, and most of the time it was, rainwater removal was higher than the controls, right? And of course, you have to understand that the experiments were done not on a rainy day, so these dynamics will change because you are making the canopy wet, and then suddenly there's sunlight and everything, and so if we have to do the experiments in real rain event, these efficacies will be a bit higher than the control, right? So what it means to grower, of course, if we use manned helicopter, we get about coverage of about 7.5 hectares in 1 hour. With mid-size platform that we used here, if we have to fly at 2.7 meter per second, because of speed was not an issue here, so we can cover up to like about 4.5 hectares, right? So in that condition, so let's talk about the air blast or archer sprayer, right? So if we have to use archer sprayer, which is what small growers use at travel speed of 0.9 meter per second, knowing that that the field is wet and is muddy, we can cover effectively about 1.5 hectares, right? So excuse me. So we definitely think that this platform can be used by small growers, and just like the air blast sprayer, note that this can do more than one thing. In given configuration, this platform can also do surgical spraying and things like that. So it's definitely complementary to helicopter, and is going to be useful for the small growers up to 250 hectares or acres farm size, right? So besides this, what's out there, I think most of you know, at UC Davis, Dr. Ken Giles, he's experimenting with this platform rather, to see the spray application efficacy from the air at different altitudes and different travel speeds in the vineyards. We think that this platform has a lot of value when it comes to applying the plant growth regulators, the surround, to avoid the apple sunburn and some other applications that we will be exploring in coming season, given that we have access to this platform, and Yama is and Digital Harvest is in the region, and they want to work with Washington State University. So some of these applications are on the card. So with that, I think this is just I just wanted to initiate the discussion, and there could be many more things that we can do with this. And again, yeah, if you have any questions, let's wait. I think after the second presentation, we'll do a Q&A, and if you have any feedback on how effectively